All right, thank you very much for watching the video, which content is an introduction to the Cointelation model, the misleading value of measured correlation, and the non-misleading value of inferred correlation. We will explain what these, sort of technical, technical jargon means later on. And lastly, we will discuss proper market conduct. There are few inspiring examples when it comes to breaking correlation misconceptions that we will go through first. If you were to take a look at these two time series, one is blue and one is red. What do you believe the measured correlation between these two stochastic processes should be? I am on purposely not giving, I guess, all the details of for you to be able to properly answer this question, but in order to break the misconceptions behind correlation, if you could write down maybe on the side of the slide what you believe the correlation between these two time series ought to be, it would be very good. So now this next slide has been taken from Wilmot's last book on interview questions for quantitative finance. I find it to be a really brilliant example as to breaking correlation misconceptions. Although this one is not really doing that, the next one is really doing that, but the idea is that the correlation between the red line here and the blue line here at the most infinitesimal level is -1. So you can sort of see that whenever the blue line is going up, the red line is coming down, and then you have like two different drifts for these two stochastic processes, and the correlation is -1. Now, if you were to take a look at the next slide, you can sort of see that the drifts are exactly the same, so going in different directions. So this one is going up, this one is coming down. But in this situation, the correlation between the red line and the blue line, the returns of the red line and the blue line, is actually -1, +1. So you can sort of see that the red line goes up whenever the blue line goes up, and you can sort of see that whenever the red line comes down, the blue line comes down as well. And eventually, there's some sort of opposite drift that is created. But obviously, this goes against the intuition that the correlation should be -1 when it is really 1. And this last example is some sort of hybrid between the last two slides. You can sort of see that at the very, very beginning, this is the example from the previous slide. Whenever the red line goes up, the blue line goes up, and whenever the red line comes down, the blue line comes down. And halfway through the example right here, especially right here, if you can sort of see here, you can see sort of the reverse happening. So whenever the blue line goes up, the red line comes down, and vice versa. And the correlation at the most infinitesimal level between these two time series happens to be 0. Now, if you come back to this slide, so this is the very first slide that we've looked at, what do you believe that the correlation at the most infinitesimal level between the red line and the blue line, the returns of the red line and the returns of the blue line, ought to be? If your answer has changed from the very first slide, then write it down somewhere. If not, then wait for the answer. By the way, just to make it a little bit mysterious, whether you're in New York, in London, in Hong Kong, whether your answer is 0, -0.5 or +4.5, all of you are correct. And this is one of the properties of the Cointelation model. It hits the whole correlation spectrum depending on the time scale. We'll delve a little bit more into this later on. So now we will be modeling relationship between assets. We'll go through very simple, two very simple examples that are quite well known in the industry. So first, the correlation model. So if you have done the CQF, or if you have done a master's in quantitative finance, you have seen this 1,000 times. Two Brownian are correlated if you can sort of define the Brownians this way. So they're correlated with respect to the rho parameter here, and then you define correlated sort of Brownian motions this way. So we will be using, as you have guessed, Pearson's correlation sort of formula here for the rest of the presentation. I'll sort of urge you to take a look at the literature around correlation. There's tons of things that have been said, tons of ways of defining correlation, but we'll be using this very simple definition. Now, what I have been calling the cointegration model is, I guess, the closest thing to mean reversion. So you have two stochastic processes here. I guess let's try to make it a little intuitive for people. So you have dst over st, which follows some sort of pure Brownian motion, and then you have in red here dst2, which is mean reverting around this stochastic process. So if you are familiar with the Einstein-Uhlenbeck model, in here you would have in blue the st, oops. So you would have this st, which is the one above, plus sigma st dwt. Let's put an st2 here. So basically, if you were to plot what these things look like at an example of what these two things should look like, if this is time and if this is sort of the value of your stock, let's say st or st2, then if you assume that st is some sort of macro leading indicator, then dst mean reverts around st. So what happens is that whenever the difference between these two guys is significantly bigger than 0, the deterministic side of the differential equation, stochastic differential equations, takes the ascendant over the stochastic part, and things have a tendency to mean revert. So you have a tendency to have something like this. Okay? So this is what I call the cointegration model. It's not exactly the cointegration model which you might be familiar with, but when it came to sort of using or naming the Cointelation model, I was trying to look at the closest mathematical models which tries to capture the essence of this Cointelation model, which is mean reversion with some sort of correlation flavor. Measure correlation of co-integrated pairs. So that sort of example I gave you in here, this is what I call the co-integrated pairs. So their spread sort of mean reverts, if you want to talk a little intuitively. You have three lines here, three time series, one red one, one blue one, and one green one here. I don't know whether you can sort of see it here, but very, very close to the blue line. And the question is, what is, in your opinion, the measured correlation between the red line and the blue line and the red line with the green line? The answer is that at the most infinitesimal level, the correlation between the blue line and the red line is 0.92, and the correlation between the returns of the blue line and the green line at the most infinitesimal level is 0.21, which sort of goes against this intuition, because you can sort of see that the green line here never really departs very far from the blue line, so you would assume that the measured correlation between these two time series is much higher. However, if you were to measure correlation at the most infinitesimal level, you would see, you can verify that for these two examples, it's of 0.92 and 0.21. This is because measured correlation is misleading when it comes to co-integrated pairs, and is somehow function of the slope of the leading indicator. So if we are to go back here in this example that we've sort of discussed earlier, if I were to sort of draw back these guys, the blue line here obviously can do all sorts of things. It's a Brownian. It's a function of a Brownian motion. So it could be doing this. It could be doing sort of that. It could be doing sort of something like this, right? But what happens is whenever this sort of process by chance happens to be going in the same direction, so either upwards or downwards, then the lagging indicator here, which is ST2, always tries to catch up to some sort of stochastic process here, which goes up by chance. So the measured correlation that you will get here, because always ST tries to, so this is ST2 by the way, ST2 always tries to catch up to ST, so you will get a high measured correlation by chance because of the shape of the first sort of Brownian motion. Okay, so the steeper the slope, the higher the measured correlation for co-integrated pairs. So the reverse is true. So the more unclear the slope, the lower the measured correlation. And this is some sort of one example of unclear Brownian motion with an unclear sort of drift. So you can already guess some of the errors associated in model selection if you assume that your sort of mathematical model follows sort of the correlation model, and you're really in a situation where there's some sort of physical connection between your assets. So for example, if you're doing pairs trading, or if you're trying to model relationship between commodities and their equities mirror, then measuring correlation could be very, very dangerous, because you could be having a very, very small measured correlation where the relationship is actually quite strong. And this aims at exposing that sort of issue. You have in here a histogram of related to the correlation model, and here you have a histogram related to the cointegration model. Just let's put it in. And you can sort of see that for the same risk, so the way these sort of these sets of stochastic differential equations has been set up is through a goal-seek function, which aims at getting the same var and then measuring consequently what the correlation between these two time series were with the same var. So you can sort of see here that for a var associated to a correlation between two assets around the point, I guess, 91 or 0.92 mean here, you have, for co-integrated pairs, a correlation which is more around the 0.5 sort of mark. So you can see that you could be having two co-integrated pairs which would have the same risk as two correlated pairs of correlations around the 0.91 mark. Obviously, if you're a portfolio manager, these kind of numbers can be extremely scary. Now, let's go to the Cointelation model. So when it came to deciding how to name the Cointelation model, I was just trying to do it as simple as possible. If you sort of can see in here, it's just a bit dumb, to be quite honest, but for the lack of a better name, I just thought that was good enough for what I was trying to achieve. So the first few letters correspond to the cointegration model, and the last few letters correspond to the correlation model. So you can intuitively sort of see that it's a model which combines both features of mean reversion and correlation. And this is exactly what this stochastic sort of this set of stochastic differential equation is trying to do. So you can sort of see in here that you can recognize the speed of mean reversion from that sort of co-integrated pairs, but you can also see that it has some sort of features of the correlation model here. Okay. By basically changing, by basically setting this row parameter here to -1, and this is the example, the very first example we saw, you can sort of hit the whole correlation spectrum. So it's a little bit small here, but if you zoom in, you can sort of see here that this represents time scale, and here you have +1, and here you have -1, and this represents a measured correlation. So you can sort of see that these two time series, depending on the time scale of choice, hits the whole correlation spectrum. And this is what I was trying to mean by whether you have guessed 0.5 or -0.5 or +1 or -1 or 0. You're all sort of right, but you're all sort of incomplete in the way you have given the answer. So now this is quite elegant, but how is this useful? We'll see that next, but before doing that, let's just emphasize it a little bit. In here, if you have the leading sort of stochastic differential equation model, and in here you have the three different models, you can see that this model here is the cointegration model. So you can sort of see the mean reversion here, the mean reversion speed appearing here. And this is the Cointelation model. You can sort of see that the speed of mean reversion appears here as well. And here you have the correlation model. You have the correlation parameter appearing here, and you can sort of see that it also appears in the Cointelation model. Now we'll introduce the concept of inferred correlation, which is sort of the immediate industry usable mirror of the Cointelation model, because as we have sort of seen, this stochastic set of differential equations, although depending on your background, whether you find it difficult or not difficult, is somehow, I guess, not, I guess, directly useful if you have hard time estimating the parameters. So what you can do instead is to define some sort of inferred correlation model, because correlation is something which is ubiquitously used in the financial industry. So you want to use something that is more or less close to this concept, and this is where inferred correlation sort of becomes useful. And this is the formula for the inferred correlation formula in here. Okay, so basically the expectation of the soup of rho t. So rho t represents the measured correlation at timescale t. So rho 1 would be the measured correlation at the, I guess, on the daily, with the daily returns. Soup in continuous time corresponds to the max function, which is which sort of appears here. And in that inferred correlation formula, you can sort of see the rho parameter appearing and the theta parameter appearing again as well. So if this is the stochastic differential equation, and if this is the inferred correlation model, so inferred correlation, and if this is the cointelation model, you can use the estimator you've sort of you've estimated, for lack of a better word, for the cointelation model in order to get an expectation for the soup of rho t, which happens to be the inferred correlation concept. So just to emphasize, if you are trying to, if you have already built risk systems which are based on the correlation model, and but you sort of like the cointelation model, you want to reuse these correlation models, you can use the concept of inferred correlation here and plug in wherever you use correlation in your current models, the concept of inferred correlation, in order to get pretty much, or like get the idea or the essence of the cointelation model in your risk models. Now, when it comes to defining or testing for cointerrelated pairs, sorry, in the previous slide here, something that you can do is to check whether the max function, so the max function of your correlation is the blue line here. So if you can sort of follow my pen here. So this is the max function. If your max function, your empirical max function, follows your soup function, so the soup function is this red line here, then you have a very strong case for the first step of the cointelation model. The second step here is related to the number of crosses that you get in cointerrelated pairs. So these two lines here, the red and the blue line, are cointerrelated, and the number of crosses that they get is much higher than if they were following the correlation model. And this sort of concept is specified by this equation here, where theta represents the speed of mean reversion and L represents the length of your data. So there's a function which gives an expectation of the number of crosses based on the speed of mean reversion and how long your data set is. So this is what I was trying to say earlier. The speed at which the max function and the soup function increases for cointerrelated pairs is much steeper or much faster than if you have two correlation models. So there's a qualitative part of the definition which usually lacks in quantitative finance. Basically, you could be using very, very elegant models, very elegant mathematical models, Unfortunately, if there's no common sense behind them, sometimes, you know, although in the eyes of a mathematician you could be making something very elegant, when it comes to a pragmatic sort of approach, you could be really failing. And this is what this is attempting in doing. So there's a qualitative part for cointerrelated pairs, which is related to the physical relationship between assets. So there must be some sort of physical connections between the assets that you're trying to test. So for example, if you're a pairs trader in equities, you could be trying Walmart and Target because they're in the same sector. If you're a hybrid trader, you know, there's some sort of physical relationship between BP and oil. Therefore, you have some sort of strong case of mean reversion between these two different assets. And the second point, so this is the first point I was mentioning. The second point here is in terms of model bias. Usually we say, well, oh, this doesn't really work, therefore we're going to be using correlation. This cannot be the case because, as we have seen here, correlation is, the correlation sort of family is a subset of the Cointelation model. Therefore, especially if you put theta here, the speed of mean reversion equal to 0, so this is in here, if you were to put this equal to 0 and therefore sort of erase this part, then you would have, obviously this is not, this is the cointegration model, but you would have, let's just try to do it properly. So for the Cointelation model, let's just do it in another color. So you would have rho dwt plus 1 minus rho squared dwt independent. Sorry, so this is the same dwt as here, obviously. And then you close this down. So this would be the Cointelation model. So in this case, if you set this guy to 0, you can sort of see that you are back to the correlation model. So this tries to emphasize on the fact that you ought not to use the correlation model whenever you feel that the Cointelation model is not the right one. Maybe there's another model which is more relevant, but correlation shouldn't be one because, again, it's just a special case of Cointelation. So this is the summary of the test. So you're testing here the sup function in here. So you want to make sure that the max and the sup function are sort of very much close to each other. You want to make sure that the expectation of the number of crosses follows this formula. And you want to make sure that there's some sort of, last point here, you want to make sure that there's some sort of physical connections between your two underliers.